Welcome to The Explainer. Today, we are putting on our detective hats and cracking a chemical case. We're going to be taking a look at one of the most powerful analytical tools in all of modern science, a machine that can find the tiniest, and I mean tiniest, trace of a substance in, well, pretty much anything.
So let's just jump right in. How in the world do you find a needle in a haystack when that needle is just a single molecule? I mean, think about it. You could be a forensic scientist at a crime scene, maybe an environmental chemist testing water. You're hunting for one specific substance, and it's buried in this complex soup of thousands of other things. Where do we even start?
Well, the answer lies in this amazing high-tech partnership, gas chromatography-mass spectroscopy. You'll hear it called GCMS for short. And honestly, this thing is the gold standard. It's what scientists use to separate and identify pretty much anything in even the most complicated mixtures. We're talking everything from drugs and toxins to, the very compounds that give your morning coffee that amazing smell. Okay, so to really understand how GCMS works, it's best not to think of it as one machine. Instead, think of it like a two-part detective duo. You've got the separator and the identifier, and each one has a super specific job. All right, so first up, you've got the gas chromatograph, the GC. This is our separator. Its whole job is to take this messy, chaotic crowd of molecules and basically act like a bouncer, forcing them into a perfectly neat single-file line. Then, once they're all sorted, they get passed one by one to the second partner, the mass spectrometer, or MS. This is our identifier. Its job is to look at each molecule in that line and figure out exactly what it is. So let's get into that first stage. How does the GC actually get all those molecules to line up so nicely? Well, it's pretty cool, actually. It sets up what we can call the Great Molecular Race. Okay, so what happens is your sample gets injected into the GC, where it's heated up and turned into a gas. That's a super important step, by the way. Then, this gas gets pushed through this really, really long, super thin tube, which is called a column. Now, here's where the race begins. Some molecules, the speedy ones, just zip right through. Others, well, they kind of lag behind because they interact more with the inside of the tube. And that difference in speed, that's the secret sauce. By the time they get to the finish line, they've all separated out and they exit one by one, perfectly sorted. All right, our chemical suspects are all lined up nice and neat. So now it's time for our second detective, the mass spectrometer, to get to mark. This is where we start creating a molecular fingerprints. The real interrogation begins.
So here's the thing. The mass spec can't really see a neutral molecule. To grab onto it and figure out what it is, it needs a handle. So the first critical step is to give that molecule an electrical charge. Basically, it has to zap it with some energy. This whole process is called ionization.
And the most common way to do this is something called electron ionization. Just picture this. You've got high-energy electrons being fired like tiny little cue balls. They slam into a sample molecule and just knock one of its own electrons clean off. And this does two things. First, it gives the molecule a positive charge. But second, it makes it super unstable. So it basically shatters into a bunch of smaller, predictable pieces. And this really breaks down the whole process beautifully. So step one, you ionize it, right? Give it a charge, break it into pieces. Step two, you accelerate it. You launch all those charged fragments into the next part of the machine. Step three is separate. An electromagnetic field acts kind of like a filter, and it sorts all the pieces based on their mass-to-charge ratio. Think of it like a curve in a road. The heavier fragments are going to fly differently than the lighter ones. And finally, step four, detect. A detector at the end just counts up all the different fragments to create this unique spectrum. And this is the absolute key to the whole thing. That pattern of fragments, it's a totally unique molecular fingerprint. Seriously, no two different molecules will break apart in the exact same way. So the machine creates a chart of this pattern, and then a computer just searches through this huge library of known fingerprints, and bam, it finds an exact match. You've got your positive ID. Okay, so we've cracked the case on how it works, but now let's talk about the why. Why is this thing so important? Let's get into the real power of precision. I mean, the sheer power here is just mind-blowing. GCMS is so sensitive, it can detect things down to sub-nano levels, a sub-nanogram. To give you some perspective, that's like being able to find one specific drop of ink in an entire Olympic-sized swimming pool. It is just unbelievably precise. And because it's so powerful, you see it being used everywhere. In forensic labs, they're using it to identify tiny bits of evidence left at a crime scene. Environmental agencies use it to find pesticides in our food or pollutants in our water. And that's just the start. It's absolutely essential for drug testing, for analyzing explosives, even for testing soil samples or making sure the ingredients in your favorite food are what they say they are. And this really sums it up perfectly. This combination of traits is what makes GCMS the go-to tool for so many scientists. It's not just sensitive, it's also selective, meaning it can pluck that one single molecule out of a crowd. And on top of all that, it's super reliable and accurate. It's the whole package, which is exactly why it's considered the gold standard in so many fields. So at the end of the day, GCMS basically gives us superpowers. It lets us see the invisible chemical world all around us in just incredible detail. It really does make the unseen seen. And that just leaves us with one final big question, right? When you have a tool this powerful, what will we choose to look for next?